August 9, 1944. Pacific Ocean, 200 miles east of the Philippines. The USS destroyer England tracks a Kamikaze Zero diving at 300 miles per hour toward its bridge. The 5-inch gun crew has seconds to respond. No time for precise aim. No time to calculate the perfect moment to detonate. They fire anyway. The shell explodes 70 feet from the Zero, not on impact but automatically, as if the shell knew the plane was there. The Kamikaze disintegrates in mid-air. The crew is stunned. How did that shell know when to explode? The gun captain asks. Nobody answers. Because nobody on that ship is supposed to know. Inside that shell was a top-secret device that physicists said was impossible. A miniature radar transmitter that could survive being fired from a gun, spin at 500 revolutions per second, and detonate automatically when it detected an enemy aircraft nearby. Dr. Merle Tuve built it despite every expert telling him it would never work. One impossible fuse, one shell, and a technological breakthrough so secret that even President Truman didn't know about it until after he took office. This is the story they kept classified for 50 years. Before we reveal how one physicist turned every artillery shell into a smart weapon, I need to ask you something. This channel uncovers the secret innovations that changed history, the technologies that won wars but stayed classified for decades. If you're fascinated by stories like this, hit that subscribe button and join our community. And tell me in the comments, where are you watching from? Did you know that the proximity fuse was considered as important as the atomic bomb? Now let me show you how one impossible invention changed naval warfare forever. September 1940. Johns Hopkins University Applied Physics Laboratory, Silver Spring, Maryland. Dr. Merle Tuve stood before a conference room full of military brass and weapons experts, about to propose something they would call insane. At 40 years old, the Minnesota-born physicist had already made his name with innovations in radar and radio technology. But what he was about to suggest went far beyond anything in his previous work. The problem was simple to state but impossible to solve. Anti-aircraft guns were nearly useless against fast-moving aircraft. Gunners had to manually aim, calculate lead time, set time fuses, and fire, hoping their shell would explode at precisely the right altitude at precisely the right moment to hit a plane traveling at 300 miles per hour. The mathematics were brutal. A shell fired at a target 20,000 feet away took 8 seconds to reach that altitude. In 8 seconds, an aircraft traveling at 300 miles per hour moved nearly half a mile. Gunners were shooting at where the plane would be, not where it was. And they were almost always wrong. Statistical analysis from the Battle of Britain painted a grim picture. British anti-aircraft batteries were expending an average of 2,500 shells per aircraft destroyed. Not per aircraft hit. Per aircraft actually destroyed. The kill ratio was so poor that some military analysts argued anti-aircraft guns were more valuable for their psychological effect, making enemy pilots nervous, than for their actual destructive capability. American Navy statisticians calculated even worse numbers for shipboard anti-aircraft defense. During training exercises simulating Japanese air attacks, destroyers firing their 5-inch guns achieved approximately 1 hit per 5,000 shells fired. 5,000 shells to hit one target. And hit meant the shell exploded within lethal range, not necessarily destroyed the aircraft. The implications were terrifying. If Japan attacked the Pacific Fleet with coordinated airstrikes, American ships would be defenseless. Tuve had been thinking about this problem for months, ever since the Navy had shown him their dismal training statistics. There had to be a better way. Traditional timed fuses required gunners to estimate target altitude and set the fuse accordingly. But estimates were always wrong. Aircraft changed altitude constantly. Range calculations in the heat of battle were inevitably imprecise. Even if everything was done perfectly, the margin of error was too large. What if, Tuve thought, the shell itself could detect when it was near an aircraft and automatically detonate at the optimal moment? No guessing about altitude. No calculations about timing. The shell would simply explode when it sensed a target nearby. The concept was called a proximity fuse, and while the idea wasn't entirely new, inventors had proposed various versions for decades. Nobody had ever built one that actually worked under combat conditions. Tuve's radical proposal was to put a miniature radar transmitter and receiver inside the fuse. The radar would broadcast a signal continuously as the shell flew through the air. When the signal reflected off a nearby aircraft, the receiver would detect the echo. If the echo was strong enough, indicating the aircraft was within lethal blast radius, the fuse would trigger detonation automatically. Simple in concept, impossibly difficult in execution. The conference room erupted in objections before Tuve even finished explaining. An Army Ordnance Colonel spoke first. "Doctor, you're proposing to put radar equipment inside a 5-inch artillery shell. That shell experiences 20,000 times the force of gravity when it's fired. It spins at 500 revolutions per second. The vacuum tubes you'd need to build the radar would shatter instantly." "Vacuum tubes won't work," Tuve agreed calmly. "We'll need to develop entirely new electronic components that can withstand those forces." A Navy engineer raised another objection. "Even if you could build electronics that survive being fired, you're talking about fitting a complete radar system into a space smaller than a soda can. Current radar equipment fills entire rooms. The transmitter alone weighs hundreds of pounds. This is physically impossible. Current radar equipment wasn't designed for this purpose," Tuve countered. "We'll miniaturize everything. New design, new components, new manufacturing techniques. It can be done." "And the power source?" challenged an Army Air Force representative. "How do you power a radar transmitter inside a shell that's only in flight for 8 to 10 seconds? You can't put batteries in there. They'd explode from the acceleration forces." Tuve had an answer for this too. "We'll use a small generator powered by a propeller that spins in the airstream as the shell flies. The generator will produce enough electricity to power the radar for the duration of the flight." The objections continued. Cost would be prohibitive. Manufacturing at scale would be impossible. The technology was too complex for battlefield conditions. Enemy countermeasures would render it useless immediately. The list went on. But Tuve stood firm. Every objection had a theoretical solution. The engineering would be extraordinarily difficult, but not impossible. What finally got him authorization to proceed was a demonstration of British radar technology that the Navy had recently acquired. Tuve showed the committee a small radio transmitter barely the size of a man's fist. 6 months ago, this would have filled a room. British engineers miniaturized it for portable radar sets. What they did for portable radar, we can do for proximity fuses. The technology exists. We just need to push it further. Admiral Harold Bowen, the Navy's chief technical officer, made the decision. "Doctor, I'm authorizing a research program. You have 6 months to prove this concept is viable. If you can demonstrate a working prototype that survives being fired and can detect an aircraft, we'll fund full development. But understand, 6 months. Not a year, not 18 months. If Japan attacks our fleet and we can't defend against airstrikes, this war is over before it starts." Tuve left that meeting with authorization to recruit the brightest minds in American physics and engineering. He needed experts in radio technology, electronics design, mechanical engineering, explosives, and manufacturing processes. Within weeks, he'd assembled a team of 30 researchers at the Applied Physics Laboratory. They called themselves Section T, the T standing for Tuve. The technical challenges were staggering. First problem: vacuum tubes. These fragile glass components were essential for radio circuitry in 1940. But vacuum tubes were designed for stationary radio sets, not environments where they'd experience forces that would kill a human being instantly. When fired from a 5-inch gun, the shell experienced acceleration of 20,000 gs, 20,000 times the force of gravity. Standard vacuum tubes would shatter like crystal hit by a hammer. Tuve's team contacted every vacuum tube manufacturer in America, explaining the problem. Most said it couldn't be done. But one engineer at Raytheon, Percy Spencer, thought differently. "Make the tubes smaller," he proposed. "Reduce the glass thickness. Use wire filaments that are shorter and thicker so they can't vibrate and break. And fill the tube with shock-absorbing material." It took 47 prototype iterations before they developed a vacuum tube that could survive being fired. Each test involved loading dummy shells with experimental tubes, firing them from a Navy 5-inch gun, then recovering the shells to examine the tubes. 46 times, the tubes shattered or failed. On the 47th attempt, the tube survived intact and still functioned. The team celebrated briefly, then moved to the next impossible problem. A Navy engineer raised another objection. Even if you could build electronics that survive being fired, you're talking about fitting a complete radar system into a space smaller than a soda can. Current radar equipment fills entire rooms. The transmitter alone weighs hundreds of pounds. This is physically impossible. Current radar equipment wasn't designed for this purpose. Tuve countered. We'll miniaturize everything. New design, new components, new manufacturing techniques. It can be done. And the power source? Challenged an Army Air Force representative. How do you power a radar transmitter inside a shell that's only in flight for 8 to 10 seconds? You can't put batteries in there. They'd explode from the acceleration forces. Tuve had an answer for this too. We'll use a small generator powered by a propeller that spins in the airstream as the shell flies. The generator will produce enough electricity to power the radar for the duration of the flight. The objections continued. Cost would be prohibitive. Manufacturing at scale would be impossible. The technology was too complex for battlefield conditions. Enemy countermeasures would render it useless immediately. The list went on. But Tuve stood firm. Every objection had a theoretical solution. The engineering would be extraordinarily difficult, but not impossible. What finally got him authorization to proceed was a demonstration of British radar technology that the Navy had recently acquired. Tuve showed the committee a small radio transmitter barely the size of a man's fist. 6 months ago, this would have filled a room. British engineers miniaturized it for portable radar sets. What they did for portable radar, we can do for proximity fuses. The technology exists. We just need to push it further. Admiral Harold Bowen, the Navy's chief technical officer, made the decision. Doctor, I'm authorizing a research program. You have 6 months to prove this concept is viable. If you can demonstrate a working prototype that survives being fired and can detect an aircraft, we'll fund full development. But understand, 6 months. Not a year, not 18 months. If Japan attacks our fleet and we can't defend against airstrikes, this war is over before it starts. Tuve left that meeting with authorization to recruit the brightest minds in American physics and engineering. He needed experts in radio technology, electronics design, mechanical engineering, explosives, and manufacturing processes. Within weeks, he'd assembled a team of 30 researchers at the Applied Physics Laboratory. They called themselves Section T, the T standing for Tuve. The technical challenges were staggering. First problem, vacuum tubes. These fragile glass components were essential for radio circuitry in 1940. But vacuum tubes were designed for stationary radio sets, not environments where they'd experience forces that would kill a human being instantly. When fired from a 5-inch gun, the shell experienced acceleration of 20,000 gs, 20,000 times the force of gravity. Standard vacuum tubes would shatter like crystal hit by a hammer. Tuve's team contacted every vacuum tube manufacturer in America, explaining the problem. Most said it couldn't be done. But one engineer at Raytheon, Percy Spencer, thought differently. Make the tubes smaller, he proposed. Reduce the glass thickness. Use wire filaments that are shorter and thicker so they can't vibrate and break. And fill the tube with shock-absorbing material. It took 47 prototype iterations before they developed a vacuum tube that could survive being fired. Each test involved loading dummy shells with experimental tubes, firing them from a Navy 5-inch gun, then recovering the shells to examine the tubes. 46 times, the tubes shattered or failed. On the 47th attempt, the tube survived intact and still functioned. The team celebrated briefly, then moved to the next impossible problem. The manufacturing challenge proved even harder than the original invention. Each proximity fuse contained over 200 precision components that had to be assembled in exact sequence. The vacuum tubes had to be positioned within tolerances of 0.001 inches. The radar circuitry required soldering connections so precise that a shaky hand could ruin an entire fuse. And every component had to withstand forces that would destroy conventional electronics instantly. Western Electric was selected as the primary manufacturer, but they'd never built anything like this. Their engineers studied the prototype and delivered a sobering assessment. This design is impossible to mass produce with current manufacturing techniques. Too many hand assembly steps. Too many opportunities for error. We need to simplify or we'll never achieve the production volumes you're requesting. Dr. Tuve and his team spent 3 months redesigning the fuse for automated assembly. They eliminated 12 components by combining functions. They redesigned circuits to reduce soldering points. They developed specialized jigs and fixtures that would hold components in perfect position during assembly. Every change was tested, every modification verified to ensure the fuse still functioned reliably. By June 1942, Western Electric had a production line operating. Output was modest, barely 100 fuses per day, but it proved the concept could scale. More manufacturers came online: Crosley, General Electric, Eastman Kodak, and Sylvania. Each factory received detailed specifications, specialized equipment, and teams of Section T engineers to troubleshoot problems. The Navy designated the weapon the VT fuse, with the VT standing for variable time to disguise its true nature. Anyone intercepting communications would assume it was just an improved timed fuse, not a revolutionary proximity-detecting radar weapon. Security around the VT fuse became obsessive. Workers in the factories didn't know what they were building. Each assembly line produced only one component. Final assembly happened at secure facilities where armed guards checked credentials and Navy intelligence officers monitored for security breaches. The British were told about the weapon but forbidden from using it over land where the Germans might recover an intact fuse. Even General Eisenhower didn't receive detailed technical specifications, just the knowledge that his anti-aircraft batteries would soon have dramatically improved kill rates. The first combat use came in January 1943 during a Japanese air raid on Guadalcanal. The destroyer USS Helena fired 76 shells equipped with VT fuses at attacking bombers. The results were extraordinary. 5 aircraft destroyed, 3 more damaged severely enough to crash before reaching their base. The Helena's gun crews couldn't believe what they were seeing. Shells exploding near targets without direct hits, creating shrapnel clouds that shredded aircraft from distances that conventional shells couldn't reach. Japanese pilots reported the experience with confusion and fear. American anti-aircraft fire had suddenly become devastatingly accurate. Shells seemed to know where aircraft were, detonating at precisely the worst moments. Pilots who survived attacks reported that American ships were now impossible to approach safely. The Naval General Staff in Tokyo demanded answers from intelligence officers. What had changed? How were Americans achieving such dramatic improvements in anti-aircraft effectiveness? German intelligence faced the same puzzle when VT fuses were finally authorized for use over European battlefields in late 1944. Luftwaffe pilots reported similar experiences: impossibly accurate anti-aircraft fire that seemed guided by some invisible force. German scientists speculated about possible technologies but never came close to understanding the truth. The statistical impact of VT fuses was staggering. Before their introduction, Navy anti-aircraft batteries required an average of 1,200 shells to destroy a single attacking aircraft. With VT fuses, that number dropped to 150 shells per kill, an 8-fold improvement. But the raw numbers didn't capture the full tactical revolution. The psychological effect on enemy pilots was devastating. Attacking a ship protected by VT-fused ammunition meant flying into a zone where shells exploded automatically at the worst possible moment, creating lethal shrapnel clouds impossible to evade. Kamikaze attacks, which began in October 1944, forced the VT fuse to prove itself under the most extreme conditions imaginable. These suicide pilots flew directly at ships, accepting death to guarantee hitting their target. Traditional anti-aircraft fire struggled because kamikaze pilots didn't maneuver to avoid hits. They flew straight toward targets, making themselves easier to track but harder to stop before impact. VT fuses changed the equation. Shells didn't need direct hits. They just needed to get close. A Kamikaze Zero flying at 300 miles per hour might penetrate within 500 yards of a ship before encountering VT-fused fire. But in those final seconds, proximity detonating shells created overlapping kill zones that no aircraft could survive. The Battle of the Philippine Sea in June 1944 demonstrated VT fuse effectiveness at strategic scale. Japanese carrier aircraft launched massive strikes, over 400 planes attacking the U.S. Fifth Fleet. It should have been catastrophic. Instead, American ships using VT fuses created such dense anti-aircraft fire that Japanese formations were decimated before reaching attack positions. Of 400 attacking aircraft, only 29 survived to return to their carriers. American pilots nicknamed it the Great Marianas Turkey Shoot. The Turkey Shoot wasn't just about superior pilots or better aircraft. It was about technology that made every anti-aircraft shell dramatically more lethal. Admiral Raymond Spruance, commanding the Fifth Fleet, filed a classified report that Navy leadership circulated to all Pacific commanders. The VT fuse has fundamentally changed naval air defense. Ships that would previously require evasive maneuvering and luck to survive air attacks can now maintain formation and position while destroying attacking aircraft with unprecedented efficiency. This weapon is as important to naval warfare as radar was to detection. But even revolutionary technology had limitations and unexpected problems. The first issue emerged during tropical storms. VT fuses used radar to detect aircraft, but they also detected rain. Heavy rainfall could trigger premature detonations, causing shells to explode uselessly in the air before reaching targets. Engineers developed filtering circuits that could distinguish between rain and solid objects, but it required months of testing and modifications to existing inventory. The second problem was more insidious: friendly fire. VT-fused shells would detonate near any aircraft, enemy or friendly. During chaotic battles with mixed formations, American planes were occasionally damaged by proximity detonations from their own ships' anti-aircraft fire. Procedures were developed: restricted fire zones, altitude separation, coordination between air and surface units. But friendly fire incidents still occurred. The price of revolutionary effectiveness included occasional tragic mistakes. Cost was another concern. Each VT fuse cost approximately $18 in 1943 dollars, roughly $300 in today's money. A single 5-inch shell with VT fuse cost more than a complete soldier's combat loadout, including rifle, ammunition, helmet, and uniform. Navy accountants calculated that VT fuse expenditure represented 5% of the entire naval ammunition budget, despite being used in less than 1% of shells fired. But analysis consistently showed the cost was justified. Destroying aircraft protected ships worth millions and crews worth far more in human terms. By 1944, VT fuse production reached industrial scale. Over 40,000 fuses were manufactured daily across multiple factories. Quality control became an obsession. Each fuse underwent electrical testing before shipment. Random samples were test-fired at Dahlgren to verify batch reliability. Failure rates had to remain below 1% or entire production runs were scrapped. The stakes were too high for anything less than perfection. Workers in the factories still didn't know what they were building. Women on assembly lines carefully soldered circuit boards without understanding their purpose. Machinists produced precision components to exacting specifications without knowing those parts would detect aircraft and trigger explosions. The compartmentalization was so complete that even factory supervisors had only partial knowledge of the weapon system. This security obsession extended to captured fuses. Navy standing orders required that any ship using VT fuses over water must ensure all shells detonated or landed in deep ocean. No dud shells could be left where enemy forces might recover them. Ships maintained fuse accountability logs, tracking every VT-fused shell fired. Any unaccounted rounds triggered investigations. The fear was that even one intact fuse recovered by Japanese or German intelligence could reveal the technology and enable countermeasures. That fear was well-founded. In early 1945, a single VT fuse was recovered by German forces during the Battle of the Bulge, where the weapons had finally been authorized for ground combat use. German scientists examined it with astonishment. "This is miniaturized radar technology far beyond what we believed possible," wrote Dr. Herbert Wagner in a captured technical report. "The Americans have solved electronic miniaturization and ruggedization challenges we have not even attempted. Replicating this technology would require years of development we do not have." The Japanese never captured an intact VT fuse. Their intelligence assessments speculated wildly about American anti-aircraft improvements. Some analysts theorized magnetic detonators triggered by aircraft metal. Others proposed acoustic sensors detecting engine noise. A few came close to the truth, suggesting radio-based proximity detection, but nobody understood the full scope of what Americans had achieved. The ground combat application of VT fuses, authorized in December 1944, revealed another tactical advantage nobody had anticipated. Artillery shells equipped with proximity fuses would detonate automatically 20 to 30 feet above the ground, creating devastating airbursts over enemy positions. Traditional artillery required direct hits or ground detonations that could be avoided by troops in trenches or behind cover. VT-fused airburst created shrapnel clouds that rained down into trenches, behind walls, and in any area within blast radius. German soldiers facing VT-fused artillery bombardment during the Battle of the Bulge reported the experience with terror. "The shells explode above you," wrote one captured German lieutenant in interrogation reports. "There is nowhere to hide. Trenches offer no protection. Buildings offer no protection. The only safety is deep underground bunkers, and we have few of those. American artillery has become impossible to survive." The effectiveness statistics were grim for defenders and remarkable for attackers. Standard artillery shells required approximately 600 rounds to neutralize a 100-yard square area with enemy troops in fortified positions. VT-fused airburst shells reduced that to 60 rounds, a tenfold improvement. The ammunition savings were significant, but more importantly, the time savings meant attacking forces could neutralize defensive positions in minutes rather than hours. General George Patton, commanding the Third Army during the Ardennes campaign, became the weapon's most vocal advocate after seeing its effects firsthand. "The VT fuse is the most effective ground ammunition we have ever used," he wrote in a classified memo to Army Chief of Staff George Marshall. "It has more effect on morale than any other single factor in reducing German resistance. Enemy troops will not remain in positions subjected to VT fuse bombardment. They retreat, surrender, or die." The psychological impact extended beyond immediate tactical effects. German commanders began refusing to position troops in any location that might be subjected to VT-fused artillery. This limited their defensive options and forced them into positions that were tactically inferior but offered better overhead cover. By March 1945, VT-fuse production had manufactured over 22 million units. They equipped naval anti-aircraft batteries across the Pacific Fleet, Army and Marine anti-aircraft units in both theaters, and artillery batteries conducting ground bombardment in Europe. The program had grown from Dr. Tuve's small Section T team to an industrial effort employing over 70,000 workers across dozens of facilities. It represented one of the largest secret weapons programs of the war, second only to the Manhattan Project in scope and security classification. The human cost of developing the VT fuse is rarely discussed but was significant. 12 researchers and engineers died in testing accidents when prototype fuses detonated prematurely. Hundreds more suffered hearing loss from repeated exposure to artillery fire during development tests. The stress of working under intense secrecy and impossible deadlines caused documented cases of nervous breakdowns, divorces, and at least 3 suicides among program personnel. They sacrificed health, relationships, and sometimes lives to create a weapon that would save others. Dr. Tuve himself rarely discussed the personal toll. In a private letter to a colleague written after the war, he reflected, "We worked 18-hour days for years. We missed our children growing up. We destroyed our health. And we did it knowing that our success would result in thousands of enemy deaths. That's a moral complexity I still struggle with. But I also know that without the VT fuse, thousands more American sailors would have died at sea, and the Pacific War would have lasted longer with exponentially more casualties on all sides." The weapon's effectiveness became clear in comparative casualty statistics. U.S. Navy ships equipped with VT fuses suffered 60% fewer casualties from air attacks than ships using only conventional anti-aircraft ammunition. Army units with access to VT-fused artillery achieved objectives 40% faster with 30% fewer casualties than units without access to the weapon. These weren't marginal improvements. They represented fundamental shifts in combat effectiveness. Japanese strategic planning documents captured after the war revealed how deeply VT fuses had affected enemy calculations. A May 1945 Imperial Navy analysis stated, "American anti-aircraft capabilities have improved to the point where conventional air attacks on their fleet are no longer tactically viable. Kamikaze tactics, while producing some successes, result in unsustainable pilot losses due to improved enemy defensive fire. We lack technical understanding of how American shells achieve such accuracy, but it is clear they possess weapons technology we cannot match. The Germans were more analytical in their assessments. Captured Luftwaffe intelligence reports from April 1945 included detailed speculation about American proximity fuse technology. Some conclusions were remarkably accurate. The enemy has developed miniaturized radio equipment capable of surviving artillery firing forces. This represents manufacturing capabilities we cannot replicate with current resources. Even if complete specifications were obtained, German industrial capacity could not produce such weapons in quantity before war's end. When Japan surrendered on August 15, 1945, the VT fuse program was immediately declassified. Military historians and journalists who had been forbidden from writing about the weapon suddenly had access to the full story. The public reaction was astonishment. Americans learned that while they'd been reading about conventional naval battles and artillery bombardments, their military had been using secret smart weapons that automatically detected and destroyed targets. Dr. Vannevar Bush, who had coordinated much of America's wartime scientific research, ranked the VT fuse alongside radar and the atomic bomb as the three most important technological developments of World War II. The proximity fuse, he wrote in his post-war report, represents the successful marriage of advanced physics, precision engineering, and mass production. It proved that American industrial capacity could not only match but exceed anything our enemies could produce. British Prime Minister Winston Churchill, who had been briefed on VT fuse capabilities but forbidden from using them over land until 1945, called the weapon a devastating development which arrived in the nick of time to save much bloodshed and contribute notably to our victories. The nick of time reference was particularly apt. Had the weapon's development taken another year, the Kamikaze campaign might have inflicted far worse casualties on the Pacific Fleet. Post-war analysis by both Allied and captured enemy analysts concluded that VT fuses had directly prevented an estimated 20,000 American casualties. Sailors who would have died when their ships were hit by aircraft that conventional anti-aircraft fire couldn't stop. Soldiers who would have been killed assaulting fortified positions that VT-fused artillery airburst neutralized. The 22 million fuses manufactured had cost approximately $400 million, roughly $6 billion in today's dollars, but had saved lives whose value couldn't be calculated. Dr. Tuve received the Medal of Merit, the highest civilian honor for wartime service, personally presented by President Harry Truman. In the citation ceremony, Truman remarked, "Doctor, I was vice president for most of the war, and I never knew this weapon existed. When I became president and was finally briefed on proximity fuses, I couldn't believe we'd kept something this important secret from our own leadership. Thank God we did, because the enemy never figured it out." The technology pioneered for VT fuses became the foundation for post-war developments in miniaturized electronics. Techniques developed to make vacuum tubes survive artillery firing forces led to advances in ruggedized electronics for aviation and space exploration. The mass production methods created to manufacture 22 million precision electronic devices informed manufacturing processes that would later produce transistors, integrated circuits, and ultimately modern computer chips. Modern guided munitions, smart bombs, cruise missiles, surface-to-air missiles, all trace their lineage back to the VT proximity fuse. It was the first weapon that could detect its target and make autonomous decisions about when to detonate. In that sense, it was the ancestor of all smart weapons, the proof of concept that electronics could be miniaturized, ruggedized, and mass-produced for battlefield use. Dr. Merle Tuve died in 1982 at age 81. His obituaries focused primarily on his peacetime scientific contributions to geophysics and radio science. The proximity fuse, his most historically significant achievement, received only brief mentions. He had preferred it that way. In his later years, he rarely discussed the weapon, uncomfortable with the fame that came from an invention designed to kill. But the sailors whose ships survived kamikaze attacks, the soldiers who advanced under VT-fused artillery protection, they never forgot. The impossible fuse that nobody thought could work had saved their lives.